Well, hello, here's the solutions video for the Unit 9 and 11 quiz, okay? In our first problem here, we're writing the explicit rules for a couple of them. You got your A, and then, we're just going to use this form, A plus n minus 1 times D. So our first term is 17. Our D is a negative 4 in this sequence, so rather than say plus n minus 1 times negative 4, I wrote it out this way, minus n times 1 times 4. It's the same thing. I think it's a little bit better. Even better, though, is to simplify it and write it as 21 minus 4n. In the next problem, our D is a positive number, 2.4, and so our first term is 12 plus n minus 1 times 2.4, and that's pretty good. Or you could simplify it to these numbers here. Let's move on to the next one where we got some recursive sequence definitions. Our first term is 5. Our next term is 4 times the previous term minus 2. So previous term minus 2 would be 5 minus 2. That's 3. 4 times 3 is 12. Then we put the 12 in there to find the next term. So that would be 12 minus 2 is 10. 4 times 10 is 40. And we do that one more time, putting the previous output in as an input here. 40 minus 2 is 38, and 4 times that is 152. So there's our first 4 terms, 5, 12, 40, 152. To the next problem, similar idea. Our first term is given, so to find a sub 2, the second term, I'm going to say my first term, 200 divided by 4 times 2. All right, so 200 divided by 8 is 25. Then I'm going to take 25 divided by 4 times 3. So that's 25 over 12. You might have gotten a user calculator to get that, 2.083 repeating. And then doing that one more time, taking this value as my n minus 1, or a sub n minus 1, divided by 4 times 4 now for the fourth term. And that gives me either this fraction or that decimal number right there. Okay, let's move on. The next problem there gives you an arithmetic sequence where the first term is 9 and the fourth term is 19.5. Let's see, I think I got that sort of scribbled out right here. Yeah, take a look at this. So if you think about it this way, here's our first term, then we have 9 as our first term, and then our next term is 9 plus some number, D, I don't know what it is. Next term is 9 plus 2 times D. It's like 9 plus D plus D. And then the third term, or fourth term, excuse me, is 19.5, and that's 9 plus 3 times D. If you solve this little equation, you get 3.5 equals D. So that means if D is 3.5, then our equation is 9 plus n minus 1 times 3.5. So there's our equation, or in the simplified version there, 5.5 plus 3.5 times n. There you go. In the next problem, where you're finding some sums, all right, this first sum, we have the first term and the last term, so I would like to use this formula if I could, but I don't know what n is. So I'm going to try to find n. So what I do is I take my form, right, my general form, all right, there's my general form, a sub n equals a plus n minus 1 times d, and I'm going to use that on this problem here. My a sub n is 99. That's my last term. I just don't know what the n is for that term. So 99 equals 3 plus n minus 1 times d, which is 2. This whole equation gives me, when I work it out, I get n equals 49. So I've got 49 terms. So I'm finding the 49th sum, and it's pretty easy now. I just plug in the numbers. First term, last term, divided by 2, 49. We get 24.99 as the sum. And in the second problem, we got a little bit different kind of information. We do know that n is 500 because we got the 500 multiples of 7. So our first term is 7. And our D is also 7. So multiples of 7 mean 7 plus 14 plus 21 plus 28, etc., etc. So I can just use this formula right here that's got all of that stuff in it. And so n over 2 is 250. 2 times a is 14. N minus 1 means 499. And then d is 7 times 7. I work all of that stuff out. I get 876,750 as the sum of the first 500 multiples of 7. Okie doke, let's do this next problem here in sigma notation. We see 3 over 4 plus 6 over 9, 9 over 16, 12 over 25. So we got multiples of 3 on top, and I have perfect squares on the bottom. So I have to figure out, how I'm going to put that in sigma notation. If I decide to let my index variable equal 1 and go up to n, because this just goes on forever, it doesn't really ever stop, I can write it this way. 3 times my index number k, 3 times k, because that will give me multiples of 3. 3 times 1, 3 times 2, 3 times 3, 3 times 4, etc. And then the denominator of that fraction, these are perfect squares, so I know it's going to be something squared. And if I think about that, that's 2 squared, that's 3 squared, 4 squared, 5 squared, and that's all 1 more than k. So I'm going to say that's k plus 1 squared on the bottom. And this expression right here represents that infinite long sum. Okay? My next problem is a couple of system of equations problems. Let's see, I think I got those on some other piece of scratch paper right here. So here's 7a. There's the solution, all right, 12, 3, and the solution to the other one is these numbers here. Let me come back and talk about these. Anyway, 12, 3, you work this out by multiplying the second equation by -3 and adding them up. You get y equals 3, pretty easy, and you substitute it back in, you get x equals 12. So that one's pretty easy to do. This one over here with the parabola here, take a look at this. So I've got, what I did was I substituted 2x in for y, because y equals 2x. So 2x equals x squared minus 6, and I set that equation to 0, that quadratic to 0. I solve that quadratic with the quadratic formula, and it works out to be this in exact form, 1 plus or minus the square root of 7. Well, one of the equations is y equals 2x, right? So y equals 2x means y equals 2 times 1 plus or minus the square root of 7. So that's pretty easy. If x is 1 plus root 7, then y is 2 plus 2 root 7. And if x is 1 minus root 7, then y is just 2 minus 2 root 7. So this is our, there it is. This is our set of ordered pairs in exact form. And if you went calculator on it, you would get these numbers here. 3.6, comma 7.3 maybe, and then -1.6, comma 3.3, something like that, something rounding off someplace. So there's your answer in exact form right there and in approximate form down there. Let's flip it over, do the next problem, which is the problem about Seymour Benjamin's. And let's take a look at that right here. So Seymour Benjamin's has this weird job where his hourly wage increases by 25 cents every hour. So his first hour's wages are $2 an hour, $2.25 an hour, $2.50 an hour, and $2.75 an hour. So that's an arithmetic sequence where my A is 2 and my D is 0.25. So the formula for that, the nth term formula for that would look like this. If I want to find out what the 40th term is, okay, A sub 40, that's my initial, plus 40 minus 1 times 0.25, and I work all of that out, and I get, where is it? Oh, there it is, $11.75 per hour for my last hour. Now, the sum of his total wages for the week, that's an arithmetic sum. Since I know the last term and the first term, and I know how many terms there are, there's 40, I can use this formula here very nicely for that. Okay? Oh, there's my 40th hourly wage, $11.75. Anyway, that works out to $275 in a week for Mr. Seymour Benjamin's. And if I take that $275 and divide it by 40, I get the average hourly wage of a measly $6.88. I'd say Mr. Benjamin needs to find a better job. Let's look at the system of equations right here. Here's the solutions, -4, 1, and 1/2. And if you don't, and I'll save the going through the solution to that for later in this video. So if you don't need it, you don't have to watch the last few minutes. Here's the inequalities problem. I'm sorry, my shading is backwards. For some reason, I thought that was said less than, and I shaded inside the circle. It really should be shaded all outside the circle as the solution area for this system of inequalities. Okay, it's above this dotted line here, which is this equation right there. So the dotted line graph is right there. And it should be shaded outside the circle, not inside. My mistake. I apologize for that. To find the intersections of these boundary regions right there, that's pretty easy, 0 and -4. This one over here is quite a bit trickier, though. I have to solve this system of equations. I have to find out where these two things equal each other. So that's a bit of a lengthy process. I'm taking my linear equation and putting it into y equals, so I can use substitution. So now instead of x squared plus y squared, I got x squared plus 4/3 x minus 4 squared equals 16. I'm going to carry that out. Squaring that binomial there gives me all of this. I set it equal to 0. I got this scary looking equation. But to get it less scary, all I do is multiply by the common denominator, fraction bust, and multiply by 9. I get 9x squared, 16x squared, 96x. And now I've got some actual fairly easy numbers to do. That's 25x squared minus 96x equals 0. I factor out an x. I get 25x minus 96 equals 0, and I get exactly 3.84 for one of the x values, and x equals exactly 0 for the other x value, which totally jives with my graph. There's x equals 0, and over here is x equals a little bit less than 4, 3.84 to be exact. I replace the x with 3.84 in the other equation and solve for y, and I get 1.12. So there's my coordinates for that intersection point. I'll go through the solution to that 3-variable system now, and if you don't need that, you don't have to watch this. Here we go. What I did was I took one of the equations, namely the second equation. I multiplied it times 3, and then I'm adding it to the third equation, right? So I got x in my second equation, negative 3x in my third equation. So I thought I'd just eliminate the x right away by doing that. And when I add those equations up, eliminating x, I get negative 7y plus 4z equals negative 5. So only 2 variables. That's good. But I got to do that same thing one more time with a different pair of equations. So I took my second equation times negative 2 this time and added it to equation 1, which is right there. So now x is eliminated again. I got 7y minus 10z equals 2. That's 8 plus negative 6 is 2. And now I have 2 equations with the same 2 variables. So let's look at that pair of equations. And those eliminate very nicely with negative 7y and positive 7y. Don't even have to change them. It's pretty nice. Then, so I get negative 6z equals negative 3, which means z equals 1/2. So I'll replace that z with 1/2 in one of the other equations that I got. 7y minus 10z equals 2. That gives me 10 times 1/2 is 5, so 7y minus 5 equals 2. I add 5. I finally work it out to get y equals 1. So now I've got y equals 1, z equals 1/2, and I can just replace both y and z in one of the other equations there, one of these original equations, and I work it out to get x equals negative 4. Okay, that's it. That's the whole thing. Hope you enjoyed that. Hope it was valuable. Good luck. Bye-bye.